Yes, ma'am.
Okay. So in the previous slide, we have seen the types of tensors and all preliminary things, conventions about the tensors. Now we can see the few special tensors. Actually, tensor it's a vast subject, but as per our syllabus, we restricted to tensors of rank 2, and we are dealing in continuation with the vector analysis. So we are learning certain things useful to understand this vector analysis concepts in terms of tensors. So accordingly, whichever is useful, what are all the points required for it, that alone we are covering. In that line, in special tensors, we are going to learn about alternate tensor. This is what it is. Epsilon ijk are the surfaces. See, this epsilon ijk is alternate tensor because it assumes the value 0 if all ijk values are same. If ijk, see, you know, ijk values can change from 1 to any number. If it is order of 2, then the maximum number will be 3. So among that, there will be different combinations of these numbers. So if all the three numbers are equal, like epsilon 1, 1, 1, epsilon 2, 2, 2, then the value will be 0. If there are different numbers, like 1, 2, 4, 1, 2, 3, or 3, 2, 1, like that, then it will have different value. So if ijk are equal, then the value is 0. And the value can be 1 and minus 1 also, based on the values of ijk. If ijk values are in cyclic permutation, so ijk, if it is in cyclic order, epsilon will have positive 1 value. If it is anticyclic, that means if it is changed, then it is negative. So epsilon ijk can have, it's like a function. It can have 0 value or 1 or minus 1 based on how ijk values are assigned. All ijk values are equal means 0. If ijk values are cyclic, then it is plus 1. If they are not cyclic, then minus 1 will be the value. Example is shown here. See, epsilon 1, 2, 3. And you see, epsilon, this is cyclic. 1, 2, 3 is a cyclic order. And 3, 2, 1, 3, 1. Hello, why it's not moving? Hello?
Hello, ma'am.
Yeah, yes, you hear me?
Yes, ma'am, I can hear you.
It's not moving. Wait a minute. Did you hear me?
Yes, ma'am, I can hear you.
Yes, ma'am.
Oh, okay. So you hear me, and but nothing is moving here. Wait a minute. Now do you see the slide? You hear me?
Yes, ma'am. Yes, ma'am.
Yes, ma'am.
Oh, okay. Okay, let's continue. So some examples are given here. 1, 2, 3, 3, 1, 2, epsilon 3, 1, 2, epsilon 2, 3, 1, all are in cyclic order, right? So it is 1. Its value will be 1. And here 1, 3, 2, the order is changed. It's not in cyclic order. 2, 1, 3 and 3, 1, 2. These are anticyclic. In such way it is -1.
Excuse
And
me.
this is, yes. Yes.
What is this? What are these IJK? This case.
IGK in tensors, you didn't attend yesterday's class?
I attended, ma'am.
Yes, all those numbers, for example,
Oh, okay.
yeah, maybe you forgot. See, all these suffixes, yeah, matrix. This A11, A12, A13 are elements, right? First row, first column. Likewise, when you represent any such multiple elements, you will generalize as a single element with varying suffixes. Instead of
Okay.
writing fixed suffix, I am writing a variable as a suffix and I will put summation symbol.
Okay.
Where
But
I and j can vary to 1, 2, 3. So
we
in
cannot
tensors, tell me.
we cannot express that alternate tensors as a matrix, right?
No, this tensor, see, matrix formation is allowed only in tensor of rank 2. But this alternate tensor, this is valid for tensor of any rank. So let us not speak only in terms of matrix here, because this is valid for higher order tensors also, which are not the matrices. So it need not be a matrix, but a tensor that represents multiple directions. That's why even in the later discussion, when we discussed about stress, I mentioned how the suffixes are used. These suffixes are used to represent the direction. One to represent the direction of the force and the other one to represent the direction of the normal of the area. Two directions involved for tensor of rank 2. For higher orders, 3 directions, 4 directions. So these suffixes, they represent the directions, different as many directions as they have.
Okay.
In higher order tensors. You understand? Here IJK,
So
it represents tensor of
3.
3. Yeah, here it is a
Okay.
tensor of order 3. That's why I didn't use the word matrix here. Because alternate tensor, it is valid for any higher order tensor. So it need not be only matrix element. It can even represent the directions of different parameters. In our stress case, we mentioned force direction and the area direction. Here it might be direction of anything.
Okay, ma'am.
Okay. And this is one special tensor. Another special tensor is Kronecker delta tensor. It is delta tensor which must be familiar. It should sound familiar to you. Kronecker delta tensor. It is delta L K. See, it is even correct if you write L and K as suffixes or both in upper case. Anyway, you can write. It's not just delta suffix L and prefix K. Delta Lk is equal to 0 when L and K are not equal, and the function is equal to 1 when K is L. So K and L both are same means it is 1. If K and L are different values, then the function will have 0 value. This tensor will have 0 value. This is called delta tensor. And Kronecker delta tensor, this is another special tensor. See here, example is given delta 1 1, delta 2 2. It goes up to delta n n. In all the cases, since the suffixes are same, the value should be 1. If they are different, like this delta 1 2, delta 1 3, delta 2 1, whatever it is, if the suffixes, if the indices are different, then the value will be 0. You can even represent like this delta Lk as a suffix or delta Lk both as upper indices also. Both are valid. Anyway, you can write delta, it stands for delta tensor that represents this. Okay, then we will see how these tensors, where these special tensors are useful. We studied this unit as a continuation of vector calculus. So we are going to see some vector operators, how they can be written in tensor notation. So you know dot product in vectors, right? And let us see how this dot product can be written in tensors. Here a vector is written. I can, in another word, I can say a tensor of order 1 is written. The tensor of order 1 is a vector. So A vector is A1 E1 cap plus A2 E2 cap plus A3 E3 cap. So if I want to write a vector simply as a tensor, I can write like this. See, it's a 3 component. We can write like summation A suffix some variable, this E suffix variable, and summation, that variable changes to 1 to 3. That is how we will be tempted to write. And I told you in the last class, there is a summation convention. Conventionally, summation is eliminated in tensors because it will include, if you start writing summation, throughout your page you will see only summation symbol. So in tensors, need not write summation symbol. So even without writing summation symbol, it means it will be the addition up to the maximum number, right? So leaving behind the summation, you just write AI, EI cap. This means this. So this is the tensor notation for writing a vector. So tensor of order 1, right? Normally we write vector like this. But in the tensor form, if you write like this, that itself is vector. A vector can be written this way. AI, EI cap. That means this vector. Now let's say a dot product. For that we need another vector. So let us say B. Let us first write in the known format. This is the known format for us. So B1 E1 cap plus B2 E2 cap plus B3 E3 cap. In the tensor form, we write like this. A B vector in the tensor form is BI EI cap. Right? Now let's see the dot product. A dot B, A vector dot B vector. Normally how we write A1, B1, we write, and the vectors only will get the dot product. So E1 cap dot E1 cap plus A1 B2, then E1 dot E2 plus A1 B1 E1 dot E3. I just expanded all the dot products I have taken, so we get 9 components, right? So this is a summation of a different. This is the summation of different terms. If I ask you in terms of summation, how will you write? You tell me. One of you tell me how you will write.
Ma'am, double summation.
Okay.
AI BJ EI dot EJ.
Okay. Yes. Okay. As you said, AI BJ. Up to that is correct. Right? And you said E also inside, you said that is very good. But here we know the dot product between these two will end up as 1. E1 dot E1 is 1. E2 dot E2 is 1. E3 dot E3 is 1. And what about other terms? E1 dot E2 will be 0. E1 dot E3 is 0. So wherever the suffixes are different, we get 0 value. Wherever the suffixes are the same, we get 1 value. So just recall whichever special tensor gives the same result. Kronecker delta tensor.
Kronecker delta. Yes, ma'am.
So A1 B1 into it's going to be either 1 or 0. So when it is 1, when the suffixes are the same. When it is a 0, when the suffixes are not same. So it's appropriate place where you can use our delta tensor. So you, as you said, you write AI, BJ, and here you write your delta function, your delta tensor. So delta IJ.
Ma'am, one question, ma'am.
Yes.
When the summation where we have shown a single summation sign I comma j equals to 1, can that be shown by double summation sign I 1 to 3 and j 1 to 3?
Both are same.
Okay,
Both
okay.
are same. Double summation is okay, but in tensor summation doesn't have any meaning. We will remove it.
Okay, ma'am. Yes, ma'am.
So in tensor you can remove this part. But normally in places where you don't use tensors, a summation is must. There you can use two summations, one for I and one for j. Here both are combined. Anyway, the information is mentioned I comma j. Both of them change from 1 to 3. So the meaning is given.
Okay, ma'am.
So a dot product in the tensor format is this. Even you can remove this summation and simply write ai bj delta ij. That is the tensor notation. So a dot b in tensor form is this. A vector in tensor form is this. And a dot product in tensor form is this. You got it?
Yes, ma'am.
Yes.
Okay.
Yes, ma'am.
Okay.
Yes, ma'am.
Very good. Let me move. Then let's see cross product in tensor notation. So let us recall all these things. E1 cross E1, E2 cross E2, E3 cross E3, all are zeros. When the suffixes are the same, we get zero value for cross product. When the suffixes are different, we get see E1, E2, take cross product, we get E3. E2, E3 means E1. E3, E1 means E2. So, and the next one, you know, this E2, E1 minus E3, E3, E2, E1, and E1, E3, it is going to be minus E2. You know the answer, right? So, if you look at this, how can you combine all these? Any special tensor can you use? If the suffixes are the same, you get 0. If the suffixes are in the cyclic order, you get some value. If the cyclic order, if the suffixes are in the anti-cyclic order, you get negative symbol, right? So this cross product can be written like this: EI cross EJ, you get EK, right? E1 cross E2, you are getting E3. So I am just generalizing, saying that EI cross EJ is EK. But you see, commonly there is a trend. Whenever the suffixes are same, you get 0. When the suffixes are cyclic, you get positive. When the suffixes are anti-cyclic, you get negative. And we know a special tensor to describe this, that is called alternate tensor epsilon, right? So, so I write like this. I introduce the alternate tensor into EK. EI cross EJ will be EK. So just to substitute some value, EI is 1. For example, J you take 2. So 1 and 2, then 1, 2, and you get E3, but it is a cyclic order, so it will be plus, right? So this is the exact place where you can find use of alternate tensor. Now let's try it for a common cross product between two vectors. There are two vectors as we defined earlier as A and B. And what is A cross B? Let us just expand. As in the case of dot product, let us expand. A1 B1, E1 cross E1. A1 B2, E1 cross E2, E1 cross E3, it goes on. Right? So if I ask you to write in the form of summation, you will write AI and BJ. And you know how to write E1 cross E1? It is this.
Alternate tensor.
Yeah, alternate tensor. So you get answer like this. A cross B in the tensor form, you can write like this. AI BJ, you get this. And in place of this E1 cross E1, you write this. Epsilon ijk ek. And you know there is no need for writing the summation symbol. It itself will take the summation up to the maximum number. Up to A3, B3 it will go for tensor of order 2. right? So you can eliminate the summation symbol, you can write. This is the tensor form of writing a cross product. Have you taken down?
Yes, ma'am.
Okay, okay, let me move. See the gradient on a scalar function. It's in the tensor notation. Gradient in tensor notation. You want to try this out, or I have to show? Del is taken on a scalar function, and we know we are familiar with this definition. I dou by dou x plus j dou by dou y plus k dou by dou z is the definition for del. It's taken on the scalar function. And just writing, because always we in tensor we want to write in terms of suffixes. Even x, y, z, we write like x1, x2, x3. So I, j, k we will replace with e1, e2, e3 because we want suffix and upper indices for tensors. So even e2, e3 in terms of even e2, e3, and x, y, z replaced by x1, x2, x3. So this is the common term. Instead of E1, E2, E3, I generalized it as EI and dou by dou xi. That's all. This is the tensor notation for gradient. Yeah, see how simple it is. That's why I asked whether you could do it. EI cap dou by dou xi. This is tensor notation for gradient. Even in tensors, we don't normally use much of this dou by dou x and all those things. There is another convention to replace this also. Simply use dou, that means dou by dou x. Like this, you see. Dou 1 means dou by dou x1. Dou 2 is dou by dou x2. Dou 3 is dou by dou x3. Instead of writing dou x1, dou by dou x, dou by dou x2, it's simply simplified as dou 1. So generally dou I, instead of writing in all these three, you can simply write dou I. That means dou by dou xi. That means plus dou by dou x2 plus dou by dou x3 is also there. So del can be still simplified as EI cap dou I, because this dou by dou x is still reduced as dou. EI cap into dou I. This means this. Do you understand? So if you look at this, if you come across any such expression, don't get scared. It is simply del. EI cap into dou I is del. All these are new notations. That's all. How to write del in tensor format. All new to us, but simple.
Okay, ma'am.
Next is gradient. Can you do it, or you want me to tell?
Ma'am, we can do it.
Do it. Just take a vector, some vector. I am taking W vector with the components W1, W2, W3. And you know, in tensors, we prefer to write IJK in terms of E1, E2, E3 because we are more, we want suffix and upper indices in tensors. So don't write IJK, X, Y, Z. Instead of that, you write E1, E2, E3, X1, X2, X3. So here W1 E1 cap plus W2 E2 cap plus W3 E3 cap is a vector W. And yeah, here I want to tell you, in the previous unit, we took a gradient only for scalar function, right? But gradient, yes, but I might have mentioned somewhere, gradient also can be taken as vector function. Normally in vector calculus, we won't get much occasions to do it, taking gradient on a scalar function. But when it comes to tensor, which operates with multiple directions, gradient can be taken on the vector function also. It's not wrong. So even vector calculus, if some cases, even though it's not practical, if you are asked to take a gradient on a vector, don't hesitate to do it. Just take gradient, you will get answer with vectors. That's all. IJK. So gradient can be taken on vector function also, especially these are significant in higher order tensors. So when I take gradient, I'm going to take this as dou by dou x1, right? We are going to take I into dou by dou x plus, that's what we are going to do. So del w, you are going to get this. The same, I am just expanding. E1 cap I have written as such. And this dou by dou x1 into this dou w, this dou by dou x1 I am keeping as such, and w only I am just writing. Wherever I have w, I am writing this term. W1 E1 plus W2 E2. Similarly, here I get E2 cap and dou by dou x2 I am keeping, and I am expanding this W. Plus E3 is dou by dou x3 into, instead of W I have written it. Just expanded W. Now for Cartesian system, see here E1 dou W by dou x1, these are unit vectors, right? Only W1, W2, W3, these can be the functions which can be taken as partial differentiation. So dou by dou x1 of W1, right? Plus I just take all E2, I cannot take partial differentiation on E2, so I am just taking it out and I am writing dou by dou x1 of W2. Likewise here E1 E3 into dou by dou x1 of W3, right?
Ma'am, is it just like direct product?
Yes, direct product. That's what here it is nothing, no dot product or cross product is given, no. Only E1 into this, E1 into this, because it is gradient. There is no dot or curl. So just direct multiplication of the vector we are taking. You get two vectors involved, right? You see two even, E2, all these things. So I expanded and I am getting all the 9 terms. Now you can very well write the summation form, or you can write the tensor notation. Since you have two parameters, two summations are taken. Instead of taking ij, here jk is taken. Ej, ek, dou by dou x of wk. See, generally you see this second term, E1 and dou x1, they have same numbers. E2 and W2 have same numbers. See the third term here also, E1 and dou x1 have same number. That's why while writing here the variable also, this Ej and Xj, same variable. And here E3, W3. So Ek, Wk. You understand? This is how it is written with the summation J and K varying from 1 to 3, because we have only 9 terms. J and K can vary from 1 to 3 only, and you can leave this summation symbol, and also you know how to write this dou by dou x. You need not write dou by dou x in tensor notation. It is already simplified by, yeah, right, dou only is the, oh, that's, I have not written it. I'm sorry, I have not written in that format. I just removed summation only. I forgot to write it. So you can write Ej, Ek and dou j of Wk. Ej, Ek, dou suffix j of Wk. That is del W. When you take the gradient on a vector, it comes like that. When you take the gradient on a